Hello everybody, I wanted to make a video here about the final step in Software Lab 4, and that is this full function MPU, which is microprocessing unit. And the purpose of this is what we've been building up to over this course. So we've gone through Boolean algebra and binary, and then looked into combinational logic circuits, and then tried sequential logic circuits. And the overall goal here is to set us into a spot where we understand what the fundamental elements of a computer are. So what we have here is a very tiny computer, even simpler than the first computers. Um, Sort of modeled, to my knowledge, it's modeled slightly on the architecture of the Intel 4004 from back in the 80s, 90s. We've connected a number of pieces here, and what this is for is this is the last thing you see before you go to the 230 class. And in the 230 class, we're going to look at this from a slightly higher level. We're looking at this from the standpoint of fundamental logic elements. This is, the smallest part of a computer other than getting into the details of how transistors work. Um, but we're sort of setting these at the smallest pieces that are still in the realm of computer science versus semiconductor physics. Um, and this is trying to show you the fundamental pieces of architecture that are used in computing so that you'll be familiar with these pieces when you go to 230 and you start to learn machine language, where you will be learning the rudiments of programming languages, the kind of programming that was done with the original computers before programming languages were invented. We just had certain machine instructions, and so all you can do in machine code is tell the computer where to look for a piece of information, where to look for another piece of information, and then what fundamental operation you want the computer to do on those, and then tell it where it should put that information to remember later. And that's what we're going to do here. So I'm going to describe all of the important pieces before we go here. So this right here, usually these four circuits, I leave them over here off to the side of the screen. You can see the other pieces. There's a ROM, there's a RAM, there's a write-only memory over here. Um, and we can talk about all of these. So a read-only memory, so we're going to go through memory first. So the read-only memory is a type of memory that the computer is not allowed to write into. So essentially, the information in a read-only memory has to be hard programmed in some way, perhaps because it's a memory chip that is programmed before being put into the computer. So there's perhaps a chip programmer whose job is to put important information that the computer will always need access to, and it programs that information into the ROM before the computer is built. There's other situations, but that's the most straightforward example of what would happen. We have the write-only memory, which, when it was originally used, the idea of a write-only memory is a hilarious computer science joke, because the whole point of a memory is to store information so that you can use that information, but a write-only memory is a thing that you can only write to, but you're not able to read from again. So I'll get back to the joke in a minute. So on the ROM, you can see that in this particular implementation, our computer can't change the value in the ROM, but we can pretend that whatever number we stick in here was already in it. And so then we just use this simple pin as an analog for a ROM. And the important piece of the ROM is that it takes the data here on 6, or the 6 that we've put in there. And then when it is told that we want to read and our address is pointing to address 3, that's why this is labeled as ROM 3. If we activate both of these lines, this buffer is going to allow the contents of the ROM over here to be passed onto the data bus. And we'll talk about the data bus in a little bit, but it is a thing where data can be put onto it so that other things can look at it and do things with it later. Now for the write-only memory, you can see that it's composed of a register, so it remembers things, but then the only thing we can do is, as humans, or as the controller, well, for the purposes of this, we can see the contents of write-only memory, but that information is simply displayed. It cannot be sent anywhere for further processing. And so originally a write-only memory that you write things to and then you can never look at again, the computer can never read it. That used to be a computer science joke, but it is a notation that we're using here because as an idea it actually has a purpose. A write-only memory is a perfectly functional model for computer parts that are primarily display-based. So write-only memory is a fine model for a computer monitor, or a speaker, or a printer, devices that you send information to and they project that information out to the operating humans in some format, and then that's all they do, and the information is no longer accessible to the computer. So that's what happens when, if you're playing a video game, you can pretend that your screen it's acting like a write-only memory. Information is sent to it, that information is displayed, you can see it, but the computer no longer has access. It just immediately throws away the information about the frames that the graphics card rendered. It doesn't get stored anywhere, so it's a write-only memory in some sense. So this is just a model for output devices, so we call it a write-only memory as a reference to the hilarious computer science joke, but it's fundamentally just a thing that outputs, and that's all it does. And then we have over here the RAM, which is random access memory, which is just the common term because it is the most common type of read-write memory. Of course, CDs count as read-write memory, but because we're talking about a computer here, when you're doing read-write memory, the most common type of read-write memory is RAM, and so in this diagram we're using RAM as the term for a read and write memory. And so you can see it's got the two pieces of the read and the write. It's got a buffer that determines when that information is read onto the data bus, and we have a register so that it can remember things coming in off of the data bus. Okay, and we'll talk about those two pieces when I start to manipulate our control lines here. So I'm going to draw it back over here, and these are just some more ROMs, and this is a write-only memory, and they have their own addresses. Notice here that the write-only memory and the read-only memory share an address, which is fine because one of them, stuff only happens when you're also reading, and for the write-only memory, stuff only happens when you're trying to write. And so you're never going to be reading and writing in the same clock cycle, and so it doesn't matter if they have the same address. So we have read-only memories from 1 to 4, and then our write-only memories from 0 to 3. And then our write-only memories are 0 to 1, but because RAM does both reading and writing, it needs to have an address which is not used for any read-only or write-only devices. Alright, so now we can stay on our main view here as I describe the rest of what is going on. Over here we have this 3 by 8 decoder, and its job is over here you can control the device address. I will toggle this one around a little bit. So you change the address to 3, and our 3 by 8 decoder will light up Y3. And you can see that that information is being handed to this tunnel. So this 1 produced by Y3 will be passed to every device that is connected to 3. There is only one such device, and I do have to jump over here for a minute. That device is this read-only memory 3. So you can see that it has been activated. So this is 1 enabled, but nothing interesting will happen until we are also telling the computer to read, which we'll figure out how to control in just a moment. Now over here we have the main structure. This is the computational structure right here. So this does the actual computing. Okay. Side note, we have right here a data bus indicator. So you're going to want to be paying attention to this, and I will call attention to it as we go here. And it will be changing as data is put onto the data bus, and then things which have the data bus attached to their input may read the information off of the data bus. While we need to be very careful to make sure that, we need to be careful to make sure that only the things that are supposed to read are being told to read. That's why we have addressing. So only one thing should be reading at a time. And additionally, we're going to either have one thing read or we're going to have one thing write at all clock cycles. So there are devices like this DMUX which have the data bus on their input. So if they're being told to read, they will read information in off of the data bus. And there are devices over here like this accumulator who have the data bus on their output, meaning that they will put data onto the data bus if they are activated and being told to write to the data bus. So one thing will read, one thing will write. It's possible that some things may be reading all the time, but well, okay. The DMUX is always pathing the data bus, but that does not mean it doesn't read the data bus. It just sends it along to the next step. And then, okay, the ALU is always looking at its inputs. So this register sometimes reads the contents of the data bus, and in some situations the data bus is being read into this FFALU, but usually only one thing reads at a time. I think if we're careful about it, that is actually what's going on. Oh yeah, there are certain circumstances where more than one thing is reading, but ultimately, things that remember, when you limit it only to things that remember stuff, only one thing that remembers something is going to read at a time. Some devices are always reading, and their information is just not sent anywhere unless a thing that is allowed to look at it is specifically trying to read information. So things that remember only read one at a time in one clock cycle. Okay. So to understand most of the rest of the pieces, we have the full function ALU, and this thing is just always doing computations. It's purely combinational. So information comes into all 12 inputs, and it's just always putting information onto the output. It's the job of the accumulator to control when the information that the ALU produces it only tries to remember things when the ALU is doing something that we intend for it to do. So it will constantly just be spitting out nonsense most of the time, and we just make sure that the accumulator only picks up the information out of the ALU when it is exactly the computation we want to make. Okay. This register over here, we just call it an input register. In modern architectures, there are, of course, going to be many of these, and they're not exclusive to the inputs to the ALU. The control of registers has become much more complicated now that registers are cheap. They used to be very expensive, so they had very limited purposes, but we actually now just have large banks of registers that just remember lots of information at a time. Uh, and so as computers have gotten more complicated and we need to maintain speed, it ends up all being much more complicated than this. But this is very similar to the architectures of the early computers. So this register just temporarily remembers data that is read from memory just long enough to complete a computation, which we'll see in just a little bit. And then the accumulator remembers things, and then sometimes we have this buffer here, and only in limited circumstances, when the accumulator has picked up useful information, we may then need to write that information somewhere, and this buffer keeps control of when do we need to write. So our goal here, I'm going to use some register transfer logic here, and there's not actually general agreement on what register transfer logic is. There's plenty of agreement of the register transfer level. So the operation, the register transfer level operations, are where data is stored in registers and you retrieve that information from registers, perform computations, and then send that information to other registers to remember. So that's register transfer level. Everybody agrees on that. But then register transfer logic is kind of, there's a lot of different notations. So this is the notation that I like. So we write down what register is going to remember new information. So we're going to store the result of a computation to write-only memory 0. And then over here I have written down what computation we want to perform on what registers. So what we're going to do is take the value in ROM 2, add the value in ROM 1, then subtract the value in ROM 0, and then store that result to the write-only memory 0. And we're going to do that in a measured way, and it is going to turn out to require, I believe, 5 clock cycles. So it requires 2 clock cycles to add a pair of numbers, and then it requires another 2 clock cycles to subtract a pair of numbers, and then the act of storing the result to the write-only memory requires 1 clock cycle in this particular architecture. And so we're just going to do that, and it's nice to have this in a video because then you can pause and rewind it and watch things happen. So in yours, you may have the ROMs and read-only memories and write-only memories off to the side, but I have moved them up here so that we can watch the entire process one step at a time. Alright, so the first thing that we need to do is, technically, since this is read-only memory, we have to have put the information that we want into it beforehand. So I'm going to add 5 to 6, and then we're going to subtract 3. And so as I said, it's ROM 2 plus ROM 1 minus ROM 0. And so just for making a very neat way of things working, I'm going to add 5 to 6. We're going to see the 11 at the output of the ALU. The accumulator is going to pick up that 11 and hold on to it long enough for us to subtract the result, and then we're going to store that result into write-only memory 1. Alright, so over here we have 8 special control inputs, and again we're going to be controlling the address over here in the address zone, but just to get everything nice and organized, the rest of the inputs are down here. You can kind of see what they're doing. I felt it was useful to leave these as wires so that you can see exactly where they're connected visually and see how they're related to the individual pieces. I probably should have rearranged these because the accumulator should be, well, but this goes to 2 places. This is kind of the bridge between these guys and these guys. So maybe this should have its own zone in the middle, but we're not going to worry about that right now. So these two and these two are separate, and this one sort of sits across both zones. And then these are the read-write control, that the read-write clock control that determines what are we doing on that clock cycle and when does that clock cycle happen. Over here we have control of the accumulator. When does the accumulator need to store information from the ALU, and when does it need to send its information out onto the data bus. And then we have over here controlling this ALU register and the pathing to the ALU. And then over here we have this joint. You can wipe the accumulator and the ALU register if you would like to. We will not be doing that at any point here, but it's just available for you to make things easier. When you are actually working with these, if you make a mistake, you can clear them and get them out of the way easily with this clear line. So that's what that's for. Alright, so here we are going to start performing our computation. And I mentioned how the data bus works, but there are, as you can see, the data bus is connected to 6 places right here, and then another 6 actually over here, and it connects to both inputs and outputs. But as we're going to see, everything on the data bus is well controlled. It is simply used as a general bus to send information from different places in the computation in our mini computer here. So data comes from many places to many places, and that is what the data bus is for. And so these buffers are in place of everything. These buffers appear right before every output to the data bus to very specifically control at all times whose information goes onto the bus. Only one thing can go onto the bus at a time, and so we have to be very careful as we control these. Now we are going to act as what is called the microcontroller, and the microcontroller controls the microprocessor. The microprocessor is a computer that processes data. The microcontroller tells the microprocessor what to do, and generally this will be done by a Moore or Mealy state machine is a good way of doing things. And this state machine has knowledge of the different types of operations you could want to do, and it knows exactly how to control as a response, or it knows exactly how to control things as long as you give it information about what exactly you want it to do. So this thing, you can then create a mini machine language that you can put information into memory and lay it out in a instruction possible data. So it might go instruction data data. Depending on the instruction, it might need 2 things of data. An instruction might need 1 thing of data. An instruction may need no data. And the finite state machine needs to carefully, every time you set an instruction, the finite state machine then cycles through stages where it picks up data. So if your instruction requires 2 pieces of data, the next 2 things in the program you give it had better be data. Or, it better better be data. And so then it interprets the next things as data, and then as soon as you've gone through the amount of data it expects, it will then expect another instruction. And maybe that instruction is eventually an end instruction, but it will just go through and carefully control. But we're going to do it manually so that you sort of get some practice with exactly how this thing works. All right, so this is what we're going to start now. So we want to add the number in ROM 2 to the number in ROM 1. So the first thing that we need to do with the ALU needs the information from the ROMs. And so that data is in a ROM, it has to be read. We can only read one thing at a time, so let's read ROM 2. So the first thing we're going to do is change our address to address 2, and as you can see, ROM 2 is almost enabled. We just have to tell it that we want to read. So let's do that in just a moment. So the first thing we're going to, well, no, let's tell it to read right now. And it doesn't really matter because the things that remember things will only happen on the clock. So it doesn't really matter what order we as the microcontroller arrange things. Most microcontrollers manage to do it all at the same time because it's a finite state machine, but since we're only human, we're going to control it one piece at a time. And we can already see as soon as the read line is active and the address points to 2, the read-only memory immediately, the data bus has lit up and contains the number 6. Exactly what the ROM 2 says. Okay, and I finally fixed this. This has been incorrectly labeled for a while, but it's because the demux was reversed by accident. Alright, so now we're going to go through these lines one at a time. So the ALU input A to B, you can mess around with that one. It doesn't do anything exciting. So the ALU input A/B prime determines which side of the demux the contents of the data bus are pathed. So so you can see that the second piece of information can be read directly. But because the data bus can only carry one thing at a time, that's why we need this input register. The input register's job is to remember the first thing we read long enough for the ALU to perform a computation. So ALU input A/B prime needs to be low so that the input register can observe what we're reading. The input to the ALU register, that's what this is, the ALU register right here. We want to turn that on so that this register will pick up this data as soon as the clock is triggered. Here we have an active low, clear accumulator and ALU register. So for us, we're going to leave that high because, again, since it's active low, it will only clear while this is low. So until this is left high, the clock has no control over this. So we're going to not clear for the rest of our analysis here. Then we have the input to the accumulator. We leave that off because at the moment the ALU is only producing nonsense. We haven't even told it what kind of function we want because it doesn't matter because we don't have our data yet. So this F is just junk. We don't want to send that to the accumulator right now. And we also don't want to output the accumulator because the accumulator doesn't have anything useful in it either. And we're reading anyway, so we don't want to put that data onto the data bus. So everything's good now. And this register can be, now we can clock. So we're reading the first memory element, the contents of ROM 2. We are reading that into the ALU. So we clock it. And there is our 6. So I did a full clock cycle there. Now we need to control the rest of this. So the other number we're computing with is ROM 1. So we'll change our address to 1. And now the 5, we're still reading, so we'll leave that on. Now the 5 from ROM 1 is sent onto the data bus, and we can observe it everywhere the data bus is attached to. Now we need to switch the order, or the pathing. So our gmux sends the 5 down. And now we also need to make sure that our ALU is prepared. The computation we're supposed to do is add. That is 14, or E. So we will change our instruction to E, to code E, which will tell us to add. And now we have 6 plus 5 is 11. So everything's good here. We don't want to clear. We actually don't need to input to the ALU register. It doesn't ultimately matter, but we don't want to overwrite the 6. Now, of course, the accumulator is going to pick up the 11 before it gets overwritten. So it actually doesn't matter whether the input to the ALU register is on or off, but I like to turn it off to not overwrite the 6. We don't want to output to the accumulator because, again, we're reading the 5. That would cause a conflict. But we now want to input to the accumulator because we want it to remember this 11. That's the computation. So we now clock, and the accumulator has picked up 11. Now we'll turn off the input to the accumulator. So that's our 2 clock cycles to add our pair of numbers and then remember it. That's 2 cycles. And so now we no longer need the reading. Well, we will in a moment. If we were going to write, we would then be able to turn off the read, which will... Now there's nothing on the bus. If we wanted to write from here, we could output the accumulator onto the bus, and now all of the writable devices can be activated as soon as we activate write as well as the relevant address. But we're not going to do that here, so I'm going to turn off the output to the accumulator. And what we need to do is our accumulator now remembers the 11, but the next thing we're supposed to do before we write is subtract the contents of ROM 0. And so now we have to be very careful. So to subtract, it's A minus B. So I may as well set up the ALU now. We're not going to need it at the moment because we don't have both. We need another clock cycle to get the accumulator's value, or the thing that we're reading, back around to this side. So subtract, it's important that we take the contents of the accumulator. That's our first number, and the number we want to subtract is ROM 0. And here, B is coming from this register. So the number that we subtract, the 3, is the one that needs to go here. So we're going to read the contents of ROM 0, so we change our address. Now the 3 is on the bus from ROM 0, and it's currently being passed down here, so we want to switch that around. We want this register to remember the 3. The accumulator is currently looking at junk, so we definitely don't want to replace the meaningful number that it's holding onto for us. And we need to input to the ALU register, because we want to write this 3 in here so that it can be fed to the ALU. And everything checks out, so we're ready to clock. The 3 now appears in this register, so we no longer need to read. We do want to output the accumulator onto the bus, and then the contents of the accumulator go onto the bus, and then over here from the bus we can pass them down here. Now we have 11 minus 3 is 8. We are in subtract mode, so everything checks out. Now we can input to the accumulator. So everything that you clock moves at the same time. So it will, so this register will observe the contents, will observe this 11 long enough to input to the accumulator. So until the accumulator updates, the accumulator can't change until it's not allowed to change. Like this value can't change before the accumulator has picked up the correct value, because it will change to the value at the same moment the ALU ceases to show an 8. The ALU has to show an 8 until an 8 appears here, at which point it will switch, but by then it's already locked in, so it's fine. So now we're ready to clock. The 8 will enter the accumulator, so that was our third cycle. So here comes number 4. The 8 is now here. I forgot to turn off the input to the ALU register, so the ALU register picked up the 0. But like I said, it doesn't actually matter whether this picks up the 0 or not. Everything's changing here anyway. So we'll turn off the input to the ALU register. Nothing important was lost, because the final result of 8 is right here. If we wanted the 11 somewhere, we should have written it somewhere before. But we didn't, so that's why I didn't write it to a RAM. If we wanted to hold on to it and use it later, it's got to go to a RAM. But we decided we didn't care. We're just taking 6 plus 5 minus 3, and only that do we want to write. Specifically, we want to write it to write-only memory 1. And so now, all you have to do is activate the write line. And so now, we just need to point to the location we want, which does happen to be 0. So that's the address of this. So you can see that this enable is active. The 8 from our accumulator happens to be what we want to write. So we've now got the value on the accumulator going to the data bus. It jumps up here. This register is ready to remember the 8 as soon as we clock it. And there's our result. Because it's a write-only memory, we have no access to it now. If we wanted to use it again later, we should use a RAM as our writable output instead, and then it can be used in the future. So in the interest of keeping this video short, that's all I'm going to do. You can, of course, ask me questions about this in class during our lab time. For the live students, of course, if this is the purely online section. Oh no, actually, this is going to be live online even next term. So yeah, one of my classes will be all online, in which case they would have to email me, but it's not this class. It's purely online. This one's live online. So if you need anything, you can send me a message or ask me a question during class, during our lab time. No problem. But of course, you can also go back and rewatch any parts of the video you were confused about. So I will see you all later, unless we, for some reason, have a class that's purely recorded. But I'm sure I will hear from you. And good luck. And I hope this goes straightforward enough to follow along, and that the circuits are provided are enough to cut down the time here on our Software Lab 4. But yeah, I hope you're all doing well. Another time.